Hey, ladies and gents. Today we are going to talk about how do you find limits without the aid of a graphing calculator. We are going to find limits analytically, so doing all of the work by hand. Now, all of the math, the general calculations that you're going to do, you should be able to do without a calculator. However, if you need a calculator just to do your adding, subtracting, multiplying, and dividing, that is okay. Now, I will say this is my second round at trying to film this video. It crashed about halfway through last time, so there is some writing on these notes already. I do not have a printer at home, so I can't pre-print them to rewrite on them. So I will talk through everything that I wrote. You will see that you will have some practice problems pop up on these notes. I absolutely want you to give them a go. I can see if you're doing them on my end. I can see if you are watching the entire video. So please do them. And if you have questions, let me know. And without further ado, we are going to get started here. Hopefully it doesn't crash this time around. There is a blank copy of the notes up here if you want to access them before you watch this with me. So I'm going to flip around my computer. Get this notes done so I can go outside and enjoy the beautiful day. Sorry for the crazy hair. We were already outside once today. So here we go. Finding limits analytically. So there are three general suggestions when you are trying to find a limit analytically or by hand. The first case is really the case that you should always try, no matter what. Like, this isn't a which case does this problem fit kind of situation. Case one is this fits everything. Case one is direct substitution. So why direct substitution? Well, we know that when it comes to finding a limit, the value of the function and the limit do not mean anything about each other. The fact that you can find, let's say, f of 2, or the limit as you approach 2, one means nothing about the other. However, if you have a function that doesn't deal with any of these DNE cases, then direct substitution is going to work. It's also the limit is going to happen to be the value of the function. So let's revisit. When do we have a function that, or a limit that does not exist? One is when you are heading to infinity. Now, if we think about when we head to infinity, that is going to be when we have asymptotes. When do we have asymptotes? We have asymptotes when we have a denominator equal to 0. So keep that in mind. As long as we're avoiding denominators equal to a 0, we're avoiding having an asymptote or heading to infinity. Another time that we have a limit that does not exist is when we are heading to two different places. We call that jumps. Now, jumps most often occur in piecewise functions heading to two different places. There are some other functions that naturally have these heading to two different location opportunities, but typically it's piecewise functions. We will focus on piecewise functions in a separate video because piecewise functions, well, they're special. So we'll get back to those. The third time that a limit does not exist, and I don't even know if I spelled this right, I am not a great speller under pressure, is when we have that freakout mode where the function just can't make up its mind. If that was to occur, direct substitution is not going to work anyway. So in all of these cases where a limit does not exist, direct substitution wouldn't work at that specific x value if the limit doesn't exist. So here we go. First example, just knowing what we know about functions, this is a parabola, it's a quadratic function, we have an x squared. In a quadratic function, we never have asymptotes, we never have jumps, we never have this freakout situation. So direct substitution should be no issue. We want the limit as we approach 2. So I plug in 2 and I find out, hey, my limit is equal to 19. Now, in this particular case, it also means that f of 2 is 19. And remember, though, as we said before, the value of the function and the value of the limit do not have to be the same. One indicates nothing about the other. They do not rely on each other. It can obviously happen that they are the same, but it does not mean anything if one exists and the other doesn't. In the case of direct substitution, though, it's always indicating that these two happen to be the same. Same as, well, I lied. No, direct substitution doesn't, well, we'll get back to that. Next one, we have a square root function. Now, square root functions do have a limited domain. We can't take the square root of a negative. So we want the limit as we approach 3. I'm going to plug it in, and I find out that underneath my radical, I get 25. 25 is not a negative. I'm not dealing with any weird situations on the graph. Square root of 25 is 5. Direct substitution worked. The limit as we approach 3 for this function happens to be 5. Now, for those of you thinking about what about that whole plus or minus thing, when we are finding limits, we are finding limits of functions. Functions, if you remember, have to pass the vertical line test. If we were to graph a square root function, all your calculator is going to give us is the top half of this graph down here. This bottom half would be the negative square root part. But notice, if we were to graph the negative square root, we wouldn't pass the vertical line test, meaning we're not a function. So we want to focus on functions. So we're only going to deal with the positive end of a square root function. Number 3, the limit of a trig function. Well, we can do direct substitution with trig functions. Again, knowing what we know about cosine, knowing what we know about this particular function, there are no issues of asymptotes heading to 2 different places or freaking out when it's just cosine. So I'm going to find the cosine of pi over 2. The cosine of pi over 2 means we want the x value at pi over 2 on the unit circle. That happens to be 0. So the limit of cosine of x at pi over 2, or as we approach pi over 2, is 0. Direct substitution should always, always, always be your first approach for finding a limit analytically. I'm going to let you give number 4 a try, and then we will move on to the next case. So if you want to check the answer to number 4, you will see that in the PDF of my answer key. So here we go. Next page. Next page, I am going to see if I can cover some of this work up. Next page, we are going to go to, you can see what the answer for the limit is already, but we are going to go to number 5. Our first attempt should always be direct substitution. So that is exactly what I did. DS is just my abbreviation for direct substitution. And I found out that we get 0 over 0. Now, some of you may be thinking, well, I could tell that I'm going to get a 0 in the denominator when I plug in -3 right away. So that means I'm going to have an issue because a 0 in the denominator does mean we have an asymptote. And having an asymptote does mean we're heading to an infinity, and heading to infinity means the limit does not exist. However, recognizing that you have a 0 in the denominator and not thinking about the numerator is not enough. We will talk about later on in these notes the difference between having a 0 in the numerator versus a 0 in the denominator versus both. In this case, you can see we have a 0 in both the numerator and the denominator. This is something that is important. Having a 0 in both the numerator and the denominator is what we call indeterminate form. And based on this word, we can tell that 0 over 0 indeterminate form means we cannot yet determine the limit. And the key word here is yet. Yet means the limit exists. We just need to do something else to find it. 0 over 0 exists, if you think back to algebra 2, when you have a hole in your function. Not an asymptote, but a hole. A hole, if you think about it, I'll draw myself a little picture and I'm going to show you another one. A hole, if I approach that hole, I'm still being led to the exact same y value. If you look at the tips of my pens there, they are pointing at the same place. I can't find a defined point of my function because it doesn't exist, but my graph is leading me to the same point, so the limit still exists. So how do we find that limit if direct substitution gives us indeterminate form? Factor in an attempt to cancel. Factor in an attempt to cancel. And I will graphically show you why that works here in just a second. So taking a look at this function in 5, I know I need to do X method of factoring. And I did so here. I got X plus 3 times X minus 2 in the numerator, and I brought down the X plus 3 from the denominator. I canceled those because that is where my hole is. We happen to have a hole at -3. Once I cancel, I am left with X minus 2, and so I'm going to try direct substitution again. Now that I've canceled out that hole, I'm going to try direct substitution again with my remaining factor. I plugged in my -3 because I want the limit as we approach -3, and -3 minus 2 is -5. The limit of this function as we approach -3 is -5. Now, why does that work? I'm going to hop over to my calculator. As you can see, I put the original function into my y1. I have already adjusted my window for a better view. As you probably know, your graphing calculators don't always show you a hole. I adjusted my window so that that hole shows up. If you look over at an x value, you can't tell that I'm pointing to -3. If you look over at an x value of -3 and look straight down, you can see a little blip in that graph. That's our hole. We can see we have no defined point at x equals -3. But if I go to my y equals in y2, which you notice is red, I'm going to type in what I got after I factored and canceled, which was x minus 2. So again, my original function prior to factoring and canceling is blue. My function after factoring and canceling is red. Now notice the graphs. The red graph and the blue graph are exactly the same. They are covering each other up. The difference is, and I'm going to go to my table to show you this, the blue function had a hole, the red function did not. The blue function had a hole at -3, so I'm going to go up to -3. And you can see for my original function, error, I'm not defined there. The red function is just a straight line that covers the exact same graph as my original function. You can think of factoring and canceling as eliminating the hole or filling in the hole. Once we have filled in that hole, direct substitution will correctly identify that location of the hole for us. So case two for finding a limit analytically. I'm going to go back to the notes. If you directly substitute and get 0 over 0, case 2 says this is indeterminate form. You need to factor and cancel in an attempt to find the limit. So number 2, direct substitution. I got a 0 in the numerator. I want the limit as we approach 1. So let's see. 1 cubed is 1 minus 1 squared, which is also 1. So 1 minus 1 is 0. Plus 1 minus 1, which is 0. I'm going to get a 0 in the denominator. This is indeterminate form, which means I do not yet know what the limit is, so we're going to try factoring and canceling. In this case, it's my denominator that needs factoring. I have 4 terms, so I am going to factor by grouping. I'm going to rewrite my denominator down here. And I am going to factor out a GCF of x squared, leaving me with x minus 1. I have a GCF technically in the second group of 1, x minus 1. So my factored denominator, I'm going to place it back in the denominator, is going to be x minus 1 times x squared plus 1. And I'm going to bring back down my numerator of x minus 1. This particular function happens to have a hole at 1, which is why direct substitution did not work. Well, now that we've factored and canceled, we are left with 1 over x squared plus 1, and I am going to try direct substitution again. I've canceled out that hole, so we're going to try this direct substitution again, or you can think of it as I filled in the hole. So I'm going to plug in 1, and we find out that plugging in 1 works this time. We say the limit of this function as we approach 1 is 1/2, 1 over 2. Now I'm going to do one more. Again, I'm going to let you do the last example on this page. I'm going to do number 7. First things first, always direct substitution. We want the limit as we approach the negative square root of 2. The negative square root of 2 squared is going to be 2. 2 minus 2 is 0. And in the denominator, the negative square root of 2 plus the square root of 2, also 0. Indeterminate form, we're going to try and factor and cancel. Now, I know I don't have a GCF. I don't have anything squared in the denominator. This is a linear binomial, so I can't factor. My numerator has 2 terms. I don't have a GCF. The only other option for factoring 2 terms is difference of 2 squares. I have a difference. I have 2 terms. Now, 2 may not be a perfect square, but technically with difference of 2 squares, you don't need a perfect square. You just need to be able to square root. And I think we did talk about this at some point in time in class earlier this year. So difference of 2 squares in the numerator. Square root of x squared is x. One term is a plus, or one binomial is a plus, one binomial is a minus. And the square root of 2, again, not a perfect square, so I'm just going to write it as the square root of 2. We just factored by a difference of 2 squares. I'm going to bring down that denominator. And hey, there you go. I'm going to cancel out the factor x plus square root of 2. That happens to be a whole at x equals the negative square root of 2. And I am left with x minus the square root of 2. So now that we have factored and canceled the whole, I am going to try direct substitution again. Plugging in the negative square root of 2. I got negative square root of 2 minus the square root of 2. And that gives me negative 2 square roots of 2. The limit of my function as we approach the negative square root of 2 is negative 2 square roots of 2. I want you to go ahead and try number 8. You can verify it with my answer key. Okay. Case 3. Well, again, as I said in case 1 is like an always try case. So first thing I'm going to do is direct substitution. We want the limit as we approach 0. 0 plus 1 is 1. The square root of 1 is 1. We have 1 minus 1, which is 0, over direct substitution in the denominator 0. You got it. You guessed it. We got indeterminate form. So we tried case 1, tried direct substitution. Case 2 says factor and cancel. I can't factor here. So now what? Now what do? We got indeterminate form. We know that the limit exists. We have to find it. Factoring and canceling doesn't work. Well, as much as your math teachers have preached, rationalize the denominator, sometimes having a rationalized denominator is what is causing the indeterminate form. If we can, if you will, unrationalize the denominator, direct substitution may work. So in order to unrationalize the denominator, we are instead going to try rationalizing the numerator. So we know to rationalize, I'm just rewriting my entire function over here. In order to rationalize a denominator, we multiply by the square root that's in the denominator. Now, if we have more than one term with the square root in the denominator, we multiply by the conjugate. In this case, we have the square root term and a 1. I have 2 terms, so in order to rationalize my numerator, I am going to multiply by the conjugate of the numerator on both the top and bottom. So rather than the square root minus 1, we're going to do the square root term plus 1 on both the top and the bottom. So numerator first, let's do some FOIL. And if you remember, foiling conjugates, outside, inside are going to cancel, so we really only need to do first and last. So a square root times a square root really means the square root is going to disappear, leaving us with x plus 1. And our last terms, negative 1 times positive 1 is negative 1. Now you can probably see we're going to have some terms that cancel up here, so I'm just going to go ahead and cross those out. 1 minus 1 is obviously 0. Now, in the denominator, I do recognize I could distribute that x, but similar to when we were, what were we working on where I said trig, when we were dealing with trig identities, I said, don't distribute in the denominator ever until you realize you have no other opportunities. That applies here too. I would not distribute in that denominator unless you realize you have no other option for doing anything mathematical. So I am just going to rewrite x times this conjugate over here. Now that we've canceled out these 1s up here, I'm going to cross those out. You'll notice we have a factor of x in the numerator. We have a factor of x in the denominator. Those actually happen to cancel as well, leaving us with 1 over the square root of x plus 1 plus 1. We have really unrationalized this function by rationalizing the numerator. Now that we've done that, just like in case 2, after we factored and canceled, we tried direct substitution again. I'm going to do the same thing here. Direct substitution again. That 1 in the numerator is not going anywhere. But in the denominator, when I plug in 0, because we want the limit as we approach 0, we have 0 plus 1, which is 1. Square root of 1 is also 1. We have 1 over 1 plus 1, or we get 1/2. half. The limit of my function as we approach 0 is 1/2. Now, rationalizing the numerator and factoring and canceling and direct substitution often can solve any finding limit problems you happen to have. Those would be more complicated situations, if you will. Things to not forget, though, is sometimes the most simplest things are the hardest to remember. Things I'm talking about. Don't forget about basic algebraic steps: multiplication, factoring, simplifying complex fractions, substitution of trig identities. Those things may be necessary as well. So in this case, it says find the limit as delta x approaches 0. Well, I'm going to go direct substitution first. I would get 2, and again, notice this is delta x, not x. So we have x plus 0 minus 2x over 0. That 0 is doing nothing. So we have 2x minus 2x, which is going to give me 0 over 0, or indeterminate form. Now, in this case, I don't have anything to factor and cancel. I have no rationalizing to take place. There's no rationalizing needed. I have no square roots. But don't forget the basic steps. Multiplication. Notice that 2 we can distribute. So I'm going to distribute that 2, which gives us 2x plus 2 delta x minus 2x over delta x. 2x minus 2x gone. 2 delta x over delta x. Those delta x's cancel, and we are just left with 2. I am going to do direct substitution again. Now that I've done the basic math, time to directly substitute again. I want the limit as delta x approaches 0. Well, now you may be thinking, there's no delta x to plug a 0 into. Well, if there's nowhere to plug in a 0, I'm still just going to get 2 as the value of my limit. The limit of any constant function is always going to be the value of the constant. Okay. Let's try another one. Always direct substitution first. Well, the tangent of 0, so over 0 when I directly substitute, tangent is y over x. I want y over x to be 0. And if y over x is y over x is 0, then I need to know where is my, or what, wow, I can't talk. Tangent, I'm trying to do this backwards. Where is tangent equal to 0? Sorry, I just want the tangent of 0. So let's think about the coordinates at 0. The coordinates at 0 are 1 over 0. Y over x is equal to 0. I get indeterminate form. Sorry, I was trying to solve an equation and that wasn't an equation. I get indeterminate form. Not surprising. So how do we deal with a trig function? Well, there are actually 2 more things. Those of you who are going into calculus will just have to commit to memory. There's 2 special trig limits. All of you right now, just keep this piece of paper and you'll have those special trig limits tucked in somewhere. The limit as you approach 0 for the sine of x over x is always equal to 1. And the limit as you approach 0 of this cosine function is always equal to 0. As long as you just take those for what they are, I think later on, those of you taking calculus will prove why these are what they are, but you need calculus to do that. But as long as you take those limits for what they are, you're golden. These are actually going to help us right here. So, trig identities. Using trig identities can absolutely help us find limits when we get indeterminate form. So let's see. We know, I'm just going to separate this. This is tangent of x, and I'm going to separate this and call it 1 over x. Still tangent of x over x. The reason I did that, though, is so we avoid any complex fractions. Using a quotient identity, tangent is sine over cosine. Now, the cool part about multiplication is you can kind of rewrite things however you want. I could think of this as, let's say I'm running out of room here, 1 over cosine of x times sine of x over x. I really just moved this sign to this numerator because notice what we have here. Sine of x over x. The limit as we approach 0 of sine of x over x, this is one of our special limits, is 1. Okay, so we just need the limit as we approach 0 of 1 over cosine of x. While doing direct substitution, Sorry that I'm working upward now. Cosine of 0, so the x value at 0 is 1. 1 over 1 is 1. We have 1 times 1, which is 1. That one takes a little bit more manipulation. Those of you going on to calculus, you will be continuing doing limits in practice with trig functions. So things to note, like I said here, the limit of any constant function is the value of that constant. Another property of limits is that you can take the limit of each individual factor within a function and then multiply them back together, and that would be the limit of your original function. Something, again, those of you going into calculus will continue to explore. Note, though, those of you taking BC Calc next year, you'll be expected to evaluate limits, but you're not going to get instruction in limits again. So let's kind of wrap this up because this is probably dragging on a little bit longer than some of you want. How do you find a limit analytically? Always, 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 first thing, direct substitution. Always try direct substitution. If direct substitution yields 0 over 0 indeterminate form, things to consider. Can you factor and cancel? If you can, do it. Try direct substitution again. Maybe factoring and canceling is not an option. Can you rationalize? You know if you can rationalize if you see a square root. If you can rationalize, try direct substitution again. Other things to consider if you do direct substitution and get indeterminate form. Do you have an opportunity to distribute? Do you have an opportunity elsewhere to factor that maybe didn't cancel something? Can you simplify fractions? Can you use trig identities? What other algebraic manipulations can you use? And again, these are two special trig limits that you just kind of need to take them for what they are until you learn why they are what they are. Now, if you're like, Miss P, I got it, I'm good to practice, go practice. But for those of you who are wondering the difference between a 0 over 0 versus a 0 in the numerator versus a 0 just in the denominator, let's talk about that. So I have 3 different limits up here, and actually, you will notice it's the same function every single time, but limits at 3 different locations. The limit is we approach 3, the limit is we approach -1, and the limit is we approach 6. The first step always is direct substitution. So directly substituting in this one, we want the limit as we approach 3. 3 squared is 9, minus 2 times 3 is 6, minus 3. 9 minus 6 is 3. 3 minus 3 is 0. Again, not enough to tell us it's indeterminate form yet. That's just a 0 in the numerator. 3 squared is 9, minus 5 times 3 is 15, minus 6. 9 minus 15 is -6. -6 minus 6 is -12. Notice this is not indeterminate form. This is not NOT indeterminate form. 0 in the numerator divided by anything. 0 divided by anything is 0. We didn't get indeterminate form. We got the value of 0. Direct substitution in this case worked. Getting a 0 in the numerator and a value in the denominator, 0 divided by anything is 0. The limit as we approach 3 in this case is 0. If you want to, throw it in your calculator, take a look at 3 graphically or approach 3 in a table. You will find the function is leading us to a y value of 0. 0 in the numerator means you have found the limit. 0 over anything means the limit is equal to 0. Okay, now we want the limit of this same function as we approach -1. So first things first, direct substitution. -1 squared is 1. -2 times -1 is +2 minus 3. That gives me 0. -1 squared is 1. -5 times -1 is +5 minus 6. 1 plus 5 minus 6, 0. This time we got indeterminate form. 0 over 0 means indeterminate, which means, think about all those cases we just talked about. You need to find the limit. So in this case, I'm going to try factoring and canceling. I'm going to factor really fast, x minus 3 times x plus 1 in the numerator. And in the denominator, we get x plus 1 times x minus 6. We happen to have a whole at negative 1, leaving us with x minus 3 over x minus 6. I'm going to try that direct substitution of negative 1 again. Negative 1 minus 3 is negative 4. And negative 1 minus 6 is negative 7. So our limit as we approach negative 1 happens to be 4/7. Last one, we want the limit of this same function as we approach 6. Direct substitution first. 6 squared is 36. Negative 2 times 6 is negative 12 minus 3. 36 minus 12 minus 3 is 21. In the denominator, 6 squared is 36. Minus 5 times 6 is 30. Minus 30 minus 6. This gives us 0. Notice, not the same as the first one. The 0 is not in the numerator. Not in determinant form because it's not 0 over 0. We have a number over 0. A number over 0 means we have a vertical asymptote. If we have a vertical asymptote, that means as we approach that value, that x value, in this case 6, we are approaching an infinity. And as we know, as we approach an infinity, we're approaching an idea, not a place. So we say that the limit does not exist. Limit does not exist. Zeros are very, very important as we are finding limits analytically. The location of zeros mean different things. So it's important to recognize these 3 different situations. Okay, that is definitely enough at this point. Any problems that I did not answer within the notes, you will see in my answer key. You've had problems pop up on here. There is more practice linked here on Canvas. And next time I see you, you're going to do a check for understanding. So hopefully you bared with me throughout all of that, and I will see y'all later.